So just a quick reminder about how this Posner task works. So for example, here we are looking at a peripheral or exogenous cue. This is a case where we actually have a valid cue. The cue is in the left box, and that is actually where the target appears. Now, on the other hand, this is a case of an invalid cue. So maybe we've decided that green means left and red means right. So when we see this cue, first of all, it's symbolic because it's not actually highlighting one of the boxes. So you actively have to remember what this stands for. So this is the case that we would actually call either a symbolic or an endogenous cue. So if we're expecting the right box, but then the target appears in the left, this would be a case of an invalid cue. So it turns out that in addition to the type of cue, the timing of the cue matters as well. And one of the ways that we can actually look at this is that depending on the type of cue, it turns out that there are certain stimulus onset asynchronies or SOAs that will affect whether or not you actually get a benefit from cueing. So ideally, if a good valid cue works, it should help you speed up your attentional orienting. Now, what's kind of interesting, a stimulus onset asynchrony is the time between the onset of one stimulus and the onset of the next. And what you can actually see in this figure on our y-axis, we have the benefit from a valid cue, and on our x-axis, we actually have the stimulus onset asynchrony. And what you can kind of see is that for the most part, for a peripheral cue, you actually start to see more of a benefit from an exogenous cue than you will with an endogenous one. So notice here that the peripheral cue, you start to see a time benefit um, almost immediately. That's clearly not zero, but it's clear that a peripheral cue provides a lot of benefit very early on. And that maxes out by about 200 milliseconds of a stimulus onset asynchrony. So 200 milliseconds between the first stimulus and the next stimulus. Now, on the other hand, a symbolic cue takes a little bit more time to process. You actively have to think about what that cue means. So you won't really start to see too much of a benefit until you get to a stimulus onset asynchrony of about 100 milliseconds. And then you can see that at some point, if the time between stimuli is large enough, there's not really a lot of a difference for a peripheral or a symbolic cue. But as this SOA is shorter, peripheral cues tend to have more of a benefit than the symbolic cues. So be very careful when you're planning studies, if you're looking at attention, to make sure that that you're using the appropriate cue and the appropriate timing. And one of the things that's actually kind of interesting is that your attention is designed to not really take a lot of backward glances. One of the things that we find is that after you have recently attended to an item, whether it's visual search or a portion of the Where's Waldo picture, once you've looked in one area, you're unlikely to immediately go back to that area. It's difficult to shift your attention back to that item. And this is what is known as inhibition of return. If you've searched one portion of the visual field, you're going to look at a lot of other places before you end up looking back. So now I kind of want to move on to talk about attention and visual search. Oftentimes, visual search is one of the ways that we study visual attention out in the world. Also, your textbook author is Jeremy Wolfe. Jeremy Wolfe does a lot of work with visual attention and visual search. So, of course, this was going to wind up in the chapter. So, we're going to talk about a few different types of searches. So, in this particular instance, in the first column, you are looking at what is known as a feature search. You're supposed to find the red rectangle um, depending on, and that's your target, and it's basically surrounded by distractors. Now, in this instance, it's easy to find because the colors are different. So we've got a red rectangle and the rest are blue. Here, the red rectangle is easy to find because we're solely defining it by its orientation. This is the only vertical line, the others are horizontal. And one of the things that you'll notice is that no matter how many items you actually put up for a feature search, reaction time is instantaneous regardless of whether the item is there or not. It's almost as if this particular feature pops out from the other distractors. And where it gets a little bit more difficult is when we engage in what is known as a conjunction search. So again, you find the rectangle, but you'll notice here that only looking at color is not enough. We've got red rectangles. Only looking at the ones that are upright is also not enough. So you can kind of see here we've got red rectangles that are horizontal, so we actively have to search through them. And in this case, what we find is that the more items there are, the longer it takes for you to search them. And the same is true for a search of spatial configuration, because again, we're looking at combinations of features. So a feature search is when the target is defined by a single attribute, like its color or its orientation. Conjunction search occurs when a target is defined by a very specific combination or a binding of multiple features together. So one of the things that you'll find is that kind of compared to this previous image where in a feature search items pop out and that line is relatively flat, which means that this is occurring in parallel, conjunction targets do not pop out. What we will typically find for a target that's a vertical red bar, you can see it takes a little bit more time to search this. I'm still looking for it. Clearly, it's absent from this array. On the other hand, here it's present, and you'll notice that regardless of whether it's absent or present, the more items you have and the more distractors you have, the longer it takes to search them. So this is a case of something that's known as the binding problem. So we're talking about these different features being bound by a combination and a conjunction of features. So how are we actually binding things like color, things like orientation, and things like that? So this is what's known as the binding problem. How do we take all of these separate features and then bind them together? And Anne Treisman and her colleague Gilad back in 1980 actually developed what is known as feature integration theory as a way to potentially explain the differences that we see in feature search versus a combination search or a conjunctive search. So Treisman said that we actually have a limited set of features that can be processed in parallel pre-attentively. So this means attention is not necessarily required. Part of the reason that a feature search is so easy to process is that attention is not necessary. The feature pops out, we don't have to spend a lot of time searching. So Treisman believed that things like color, that these different features of objects were stored on different maps that could be accessed in parallel. So there's a color map, there's an orientation map, maybe there's a shape map, and she called those feature maps. Now here's what's really critical. Now if I'm only looking and defining an object on the basis of a single feature, I don't need attention. But if I have to bind those feature maps together or bind those features together and search for a specific combination of features, at that point, searching the array requires attention. Go back. Okay, so some of the evidence that Treisman actually has for this is that when we don't pay attention to feature conjunctions, we have what are called illusory conjunctions, which Treisman said basically occurred when the feature maps basically combine themselves in random ways. And so sometimes you'll get a combination of features that is not actually present in the array. And she took this as evidence that binding absolutely requires attention in visual search. So what would be an example of an illusory conjunction? So let's say that I'm looking at all of these letters in different colors and then I make them disappear. I hide the image. If you saw a green H in this image, that would be a case of an illusory conjunction. There is no green H here. Now, what's important is that you're only going to make illusory conjunctions with actual features that are present in the array. You will not see a green T because there is no T in this array, and you will not see a blue H because there is no blue in this array. And Treisman actually found that the conjunctions that people made were based off of features that were present in the array, and only those features that were present in the array. And that's why it is believed these features require attention to be bound. If we're only looking at one feature, like a feature search, we don't need attention. But if we're doing a conjunction search, we do. So how does visual search work in the real world? Most of us do not spend our time looking at colored rectangles or things like these. What do? Well, one of the things that's really nice, again, is that we have experience, we have prior knowledge. And thankfully, we are going to engage in something known as guided search. We're going to restrict our search based on the features of the item. So, for example, if I am looking for apples, which are definitely in this picture, I know that apples are red, or the apples that I want are red. Honey crisp for life, y'all. What I will typically want to do, I'm not going to look at all of these rows of green and purple vegetables or the yellow vegetables. I'm solely going to search the ones that are red. So because of that, I can restrict my attention. I'm less likely to get overwhelmed, and I'm able to more quickly find what I'm looking for. And our knowledge of where we can expect certain objects to appear can also help us. So, this is what is known as scene based guidance. Our understanding of a scene and where objects are likely to be found helps us find them. So, if I'm trying to search, when I do a standard visual search here, you're going to kind of notice that in general, it's kind of hard for me to find the coffee maker or find the water faucet or things like that. So here's our water faucet, here's our coffee maker, here's our knife. Things that we would normally find in a kitchen, but when they're scrambled like this, it's hard to do. Here's a stove. I just found that. But if I'm looking at a scene that I'm very familiar with, such as this kitchen, I have a pretty good idea of where the stove's going to be located. I'm pretty sure I know where the coffee maker is located. I know where the knives will be. I know to expect bowls and mugs on horizontal surfaces and not just hanging around in random places. Although I do have to say, a basket of carrots is incredibly suspect. Now let's talk a little bit about attending items in time. This is what is known as the Rapid Serial Visual Presentation, or RSVP task. And how this typically works is you are presented with stimuli very, very rapidly. So I kind of want to show you an example of what this would look like. What we're about to do is a task that is illustrated for you right here. So you look at a fixation, you're going to look at a bunch of letters in rapid fire succession. And you are basically looking for two different targets. So we're looking for the first two letters that we see after a white letter. So you can see that these are presented very, very quickly. So where this gets really interesting is when we have a finding called the visual blink. So here I've kind of pulled this up for you. So basically you're going to detect two targets with the second target coming 100 to 600 milliseconds after the first target. The blink will occur about 200 to 300 milliseconds. So here's what we're going to do. We're going to watch the sequence. We're either going to look for an A or B, and then we're going to look for a Y or a Z. So we're going to go ahead and try this right now. Okay, I saw B, I saw Y, and I was correct. Want to try it again? I saw an A, and I saw Z. Good job. Okay, let's try another. Okay, I saw B, I saw a Y. Okay, one more. Okay, I think it was B and a Z. I got that correct. I'm kind of surprised by that. One more. This is kind of fun. Okay, I wasn't paying attention. I'm going to go with a B and a Y. I was incorrect. Now, one of the things that's actually kind of interesting, and I would encourage you to try this for yourself, is that the time can lag between those two targets. We either had to do an A or a B, so target one, and then we would have to do a Y or a Z. Now here, in this particular example, we have to notice what the letter was that was in white, and then we have to look for the letter X after that. And it turns out that depending on how quickly these stimuli are presented, we get something called the attentional blink.